So what did we learn last time? All right, so let's do some review. We talked about the nth root of unity, right? This is just something I hope you can understand its significance or its meaning, right? We know that the so-called nth root of unity is just that I have a number n, omega, is power to be the to the power n equals to 1. That's it. That is the root. And in the complex plane, right, we have the real part, we have the imaginary part. And what it really say is that if you draw a unit circle, right, this is 1, this is I, this is -1, this is -I, right? And this nth root of unity is going to reside on this circle, right? And depends on the number, the value of the capital N, then you have different density, right? And the most important is, remember, is omega equals to the power, e to the power 2 pi I divided by N. And again, do not forget that this means that omega equals to cosine 2 pi I divided by N, no I, right? Cosine 2 pi, yeah, divided by N, plus I sine 2 pi divided by N. Okay, yeah. Now, then why we need this? Because this is a very handy notation we will use in the quantum Fourier transform and also in the quantum phase estimation or Shor's algorithm. We're going to use this a lot, okay? Because in the whole quantum computing algorithm, in many of the quantum computing algorithm, we relies on playing with the phase of the basis state to constructive and destructive interference. Okay, so without loss of generality, right? We can set capital N equal to the power N. Usually in the algorithm, it's not enough. We just increase the number of bits so that you can make it into the 2 to the power small n, right? Because this n is going to usually talking about the number of qubits we need to use. Right? Depends on the algorithm, but usually this is the case, right? And capital N is usually the total number, the size of the problem. So what is quantum Fourier transform? As I said last time, it's nothing but just it has the same matrix as the discrete Fourier transform. And that's it. Okay? So it is equals to what? If you try to look at the elements of the matrix, it basically is talking about omega. Do you remember actually? What is that? Omega to the power what? For the ith j element, ith row, jth column. Yeah. Omega to the power what? Yeah, you forgot that's, yeah. Negative I times j. Right? You memorize this. Okay, and that's why, for example, this one, which row? This is row, or let me don't, yeah, row 1, right? We start from 0, and column n minus 1. And because of this, its element is omega to the -1 times n minus 1. And then what is omega again? 2 pi I divided by capital N, right? Times, and then this is negative n minus 1. And that is how we get this element. Okay? I think it would be good to memorize something, because sometimes you read paper or talk to people, go to a conference, they talk about something related to this quantum Fourier transform or whatever. This is pretty handy, and for you to correlate what's going on. You really, although you can Google, go to Wikipedia, right? Memorizing this one is useful. Is that okay? Okay, so quantum Fourier transform, you know it well. You know what is discrete Fourier transform. And in particular, if we apply this to a basis state, here J refers to a basis state. Okay, any basis states, right? So for n qubits means the small n qubits, right? The basis states run from where to what to what? for a small n qubit. This is looks like, for example, 0, I should write in the column form. Yeah, 0, 0, and then eventually 1, right? And then 0, right? And this is the jth row, right? Yeah. So if we apply the quantum Fourier transform to it, you just go through the math. You see that it becomes a superposition of all the basis states, right? From 0 all the way to n minus 1. And with, or we can say weighted by this coefficient, which is omega to the power negative jk. Okay, so again, what is a quantum Fourier transform? Yeah, it does something, but it's also just a gate after all, right? It rotates the basis states in the hyperspace. And every quantum gate is defined by how it rotates the basis states, right? Identity. What does an identity gate do? It rotates to its original position. It's still a rotation, but it's not moving, right? That's what you can. The kids like to tell their mom, right? Yeah, I'm moving, but I'm just moving no distance, right? So same, right? But here you see that it does rotate it, but after you rotate what it is, it becomes a superposition of all other basis states, which is very normal, right? You rotate a vector in the 3D space, you rotate the x hat, it will go to some position, and it must be a superposition of all the other basis vector, because you're still in that space. Make sense? Okay, and if you can memorize this, this will be great, right? Because after all, if you don't memorize this or understand this, you cannot derive a new algorithm. You cannot invent something new, right? This need to be very familiar to you. So any questions? Yeah.
So because it's the jth basis, it basically takes one column out of that entire matrix, right? If you do the multiplication.
Exactly. Very good, right? So he just said that this basically take the jth column of the UQFT, right? Because of the way we do the multiplication. Because jth vector is just 0, 0, 0, 1, right? So after this, you basically just taking the entire column. Yeah, that's what we said last time also.
So I guess in terms of looking at it from a frequency perspective, it looks like this vector now has various frequency components, right? Because we said that in the last lecture that each row in QFT would correspond to one frequency.
Yeah, you're right. If you go back to DFT, right? So let's do not. Yeah, I think we can also say that. But for now, if we're only talking about discrete Fourier transform from a time domain to a frequency domain, that is exactly what you just said, right? For each frequency, after the Fourier transform, it actually becomes the linear combination of many more frequency. And a special case is that if this is the first vector, which is 0 frequency, the DC, right? After Fourier transform, you see that it's just a constant superposition of all different frequency, right? Because this row is 1. No. Did I say something wrong? Yeah, this row is. No, this column is 1. Yeah, because it's take the first column, the 0th column. Yeah, okay. So let's move forward. Last time, I tried to prove the unitarity using a method on the fly, but I was not successful because that way I need to rely on the fact it is unitary. So we need to go back to the basics, talk about the basics of the unitarity, right? So what is the definition of a unitary matrix? Yeah, just in general, then U dagger times U dagger equal to 1, right? That is the definition. But in order to prove it, we use another definition, which is equivalent. We proved earlier already. If not, watch that video again, how to prove the matrix is unitary. Is that each column of U is orthonormal. right? So what does it mean? Let's just look at the unitary, the UQFT one more time, the quantum Fourier transform matrix, right? So I can write it as what? I wonder if you can memorize the form. What is the quantum Fourier transform? It must be 1 over square root n, right? Omega 0 times 0, omega 0 times 1, right? So particularly, I want to talk about the eighth column. So it becomes what? Omega 0 times A, yeah? And then let me talk about the bth column also is omega 0 times B, right? And then you go all the way to last column, which is 0 times n minus 1. And then for the second row, it's easy. The 0 becomes 1 because it's the first column, the J, the I, right? I mean J, we're talking about JK, so the J, right? So up to here is negative 1 times A because it's the first row, 8th column, negative 1 times B, right? And then negative 1 times n minus 1, right? We are familiar with this, and then you just keep going. Eventually, what is the last row? It is negative n minus 1 times 0, omega negative n minus 1 times 1. And let me do not write this because I don't have space, right? I just write omega negative n minus 1 times A, right? Because the 8th column, omega negative n minus 1 times B. What is the last one again? Omega negative what? N minus 1 times n minus 1, right? Because this is the the n minus 1 row and n minus 1 column, right? And then what do I mean by the vector of the column? For example, this one, right, is the column. I can represent, I say this is a vector, right? Because it has how many entries? N minus 1 or what? N, right? You start counting, right? And this one, I just call it B, right? They can be the same, I make it general. So now the goal is to find out what is A, B. I want to find the inner product of any AB, right? This is how we find the inner products, correct? Okay, so what is A if I write it in the column or vector form? How do we do it? It becomes what? It becomes a row, very good, right? But do not forget we also have 1 over n here. Okay, so it is 1 over square root n, I say wrong, 1 over square root n, right? Then this becomes omega negative 0 times A, omega negative 1 times A, dot, 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 omega negative n minus 1 times A. Is this correct? Yes. You need a conjugate, right? From here, you don't see the I, but because we encapsulate it in omega, so we do need to put the conjugate, because if we spell out omega negative 0 times A, is it actually equal to e to the power negative 2 pi divided by ni 0 times A, right? So if you do conjugate, I do need to make this negative becomes positive, right? So because of this, I do need to make this positive. Make sense? Right? And then similarly, I'm going to apply this to the bth column. This one, I'm not going to do conjugation, right? And then you multiply them. What do you get? And I forgot 1 over square root n also, right? So this becomes 1 over n. What is this, right? So first, it is omega 0 times A minus times omega minus 0 times B, right? And then 1 to one also, but it's A and B, right? So basically, this one is just summation for, let's say, I equals to 0 all the way to n minus 1, capital N minus 1. Omega I A minus B. Okay, now, the equation we learned earlier again is useful. Do you remember when we talked about the nth roots of unity? When you do a summation of I equals 0 n minus 1 omega I, and then you multiply by L, this equal to 0 if L not equal to 0 because of the destructive interference. Remember this? Right? Remember what is summation of omega to the power I, right? From 0 to mi. It means you go through the whole circle. And then if you also have this L as integer, you still go through the whole circle. They all got cancel each other. Remember this? Yeah? But what if L equal to 0? What is that? Just look at this. What is L equal to 0 when you add them together? It's 1 n, right? You have n1, right? So this one tells us that this is equal to 0 if A not equal to B, because here L is A minus B. And this equals to 1 if A equals to B, right? So this is exactly the definition of orthogonal, right? And this is the definition of normalized, correct? Yeah, so it means that it is orthonormal, right? So this matrix, every vector is orthonormal, right? It is normalized, but it is orthogonal to other column. And that's why a quantum Fourier transform matrix is unitary, which is a requirement for a quantum gate. What is A when A not equal to B? What A minus B equals to L? Yeah, if L is not 0, means A is not equal to B. Then you get 0, right? This thing will give me 0 because this is. And by the way, I think you will hate me to change again, but maybe it's better to change. I use I here. Let's do more. Use I because you may think it's square root, right? So let me call it. What should we call it? But we already have J and K confusing. But let me just call it. How about M? Yeah, you all know what I'm talking about. M, right? Let me call it M. It's up to you, right? So here I also should not call it I. It may confuse later when you study. Let me call it M. Is this okay? Right? So compare these two equations. They are the same if A minus B equal to L. And we know that when L is 0 or is not 0, when L is not 0, it means A not equal to B. It gives us 0. The sum gives us 0. Okay? And if A equal to B means L is 0, we know the sum gives us n. Then you cancel this one over n, so it gives you 1. So no, we did not. Yeah, but you look familiar because I can even test this in midterm 1. If the exponential don't cancel. We proved this last time already. This equation, not this equation. We're using the equation we proved at the beginning for the nth root of unity. Okay? So here is to show that this is a good exercise, right? It's not nothing special, but it's good exercise. What is the inverse of quantum Fourier transform? And I can tell you, okay? I can tell you, and then we prove it. The inverse of quantum Fourier transform I actually should say that, right? I first want to study this one. Let me study this one. What is for quantum Fourier transform dagger Kj? Okay, I'm talking about the kth element, kth row and jth column of the adjoint matrix. Okay, what is that? Can you tell me? I remind you, what is QFT for the JK? It is equals to e to the, let me use omega, yeah, let me use omega. The element, just the element. What is the element? Yeah, when I say JK, it means the jth row, kth column. J times K. It makes sense, everyone? So when, okay, in in that case, actually, I think it is better I call it KJ. Let me call it KJ. KJ, it's the same, KJ. Because I want to keep using the same notation. The kth row, jth column, right? It's just the same. I now call it kth row, jth column. What, after I do the adjoint matrix, right? You need to do transpose and also complex conjugate. What is the element now here? It basically is saying that I'm going to get omega negative Kj and do a transpose. So this one comes from here, right? Right? So what is the elements now? So it is equals to still minus. I mean, yeah, become plus, right? Because you're a complex conjugate, right? Becomes plus Kj. Again, the reason we can do that not because of Kj is because omega has the I inside, negative, have the imaginary inside, right? So this is becomes, and instead of Kj, I'm going to call it Jk, right? Because I'm going to swap it, right? Right? So it means that this becomes this, which really doesn't matter. I can write it as Kj. Make sense? It's just multiplication, right? I can multiply it J times K or K times J. Is the so the kth, so here is talking about the kth row, jth column of the quantum Fourier transform adjoint matrix is equals to omega Kj times Kj. That's the whole thing that we have done here. Okay? But because it is unitary, we just proved that it is unitary. Then we know that quantum Fourier transform dagger times quantum Fourier transform equal to I. And we also know that quantum Fourier transform dagger equals to the inverse of quantum Fourier transform, right? So because of this, then we know that the inverse, I can just call it IQFT instead of doing the inverse. Here I put the inverse, but I can rename it as IQ. Maybe I don't have enough space. I should not. Let me rewrite it, do it better. This is UQFT inverse equals to UIQFT IQFT, just a definition. This is called inverse quantum Fourier transform. It has a matrix which is equal to omega kj. And yeah, I keep missing something important. I should also put 1 over square root n here, right? Because I just keep looking into the element. I should put this as 1 over square root n. When I spell out the elements, right? I should put 1 over square root. Is this okay? I'm sorry for confusing you. Is that okay? Because the whole matrix should have a 1 over square root n. Any questions for this part that I'm confusing you? Is that okay? Yeah, the matrix should have a 1 over square root in front, right? So here I'm missing the 1 over square root n. Okay, so this is the matrix for inverse quantum Fourier transform. Now, if we try to just expand it instead of being so lazy, I try to write down the whole matrix, then you see everything is the same, right? This is, again, this is just equal to omega 0th row times 0, omega 0th row times 1. Because now it's jth column, right? Due to the way I wrote it here, j becomes the column. Okay, so k is the row. At the beginning, I define k is the row, right? Jth is the column. What is the last one? 0 times what? n minus 1, because it's 0th row, n minus 1 column, right? And then this is 1.0, 1.1, 1.n minus 1, because it's the first row, one row, I call it first row, n minus 1 column, right? Yeah, let me finish this. And then this is omega n minus 1 times 0, omega n minus 1 times 1, all the way to omega n minus 1 times n minus 1. You don't need to look at this, but just by compare this and this, what is the difference between quantum Fourier transform and inverse quantum Fourier transform?
Negative.
Yeah, exponents become negative. Everything else is the same. Okay? Yeah, question?
So the top.
Put what? Where? Here? This one?
Yeah, so this is matrix. You should be able to show now.
Oh no, this is, yes, you're right. I should not do this. I should actually put a bracket and say this is kj. Yeah.
Meaning this is.
Oh no.
Because you jump from one, it seemed to be like then you jump to matrix. So, or are you?
Yeah, you're right. I'm wrong. I should not do that. Actually, you're right. This is an element. This is not a matrix, right? So let's say it clearly. When I write U, this is a matrix, and then I say kj, I means the kth row, jth column element. So this is the one, right? So let's look at this. This is the matrix, but then we take the kth and j column, right? Now here, yes, here then a little bit tricky. I actually should just this I can say this is a this is not that strict, but yeah, I should say I take the transpose and then compress conjugate. So this is not a matrix. I should not put dagger actually, but it means I take the transpose, swap k and j, and put the compress conjugate.
So you did the diagram
On the matrix. Yeah, and then I actually should not still talk about this kj here, right? Because this is an element already.
we can expectation. If you think it's a matrix,
No, yeah, and unfortunately, sometimes we need to do that. I know this make you messy, right? But no, but in matrix you cannot use summation, right? Or you cannot say unless you write down all the outer products of k and j, right? So here what we are trying to do is, yeah, this is a notation. If this is the U, this is the matrix, and then we talk about the kth row and jth column, this is the element, okay? So this is correct, this is just the element. But in order to show you that I need to do the swap, now you just treat this, okay, I know what to make it straight. I remove this kj, then this becomes a matrix. Okay, so when I have a bracket closing this one, then this is a shorthand rotation, meaning the kth element, kth row and jth column has this element. The kth column and jth row has this element, and this is a matrix. Instead of writing this whole thing out, I only write the expression for the element. And now I can add the dagger, right? So yes, but it's a good exercise. I know it's messy. Let me say one more time, right? So that you don't get confused. This is the matrix, right? And quantum Fourier transform matrix. And I want to know what is the kth row and jth element. And this is the kth row and jth element. It is a scalar. Is that okay?
So then this is also.
Because you may forgot. I want to write it for your information.
So that's fine. You use the same thing here. So this is not a matrix.
And hold on, I also missed the 1 over square root n. Right? So this is an element. Okay? Now, so this is okay, right? This row? Now, then we come to here. This is a matrix. And then we take the kth row and jth element. So this is the element. And we say this is equal to 1 over square root of this matrix, taking the dagger. Yeah, so the more I do it, the more error I make. I need to do this, kj. Okay, so now this is the matrix, and then I take the kth and jth element.
This seems conflicting.
Where? No. This is a matrix, right? This is a matrix. This whole thing is a matrix. Do you agree? This whole thing is a matrix. Again, as I told you, right? How do I represent the matrix? This is the whole matrix. But I can just write down an expression to represent each row with this bracket, omega kj.
So then this is also a matrix.
No. I don't have a bracket. You need to have the bracket to be a matrix. This is just a number. Okay? So this is a matrix, right? And then here, this whole thing is a matrix. And I take the kth and jth element. Okay? And this is just shorthand rotation. I could have just copied the whole thing here, right? It's not equal to this, but I could have just write down n by n matrix, right? Is that okay, everyone? Right? So, and then now I can do the transpose. I know I just swap it, and then I do a dagger, right? And that's why it becomes positive. And now I'm not writing the matrix. I just think that the kth and jth element becomes jk, right? And I can swap this become kj. Okay? So the conclusion is that the kth row and jth column of the adjoint matrix of quantum Fourier transform is omega kj. And then I proved that, we showed that we know it's unitary and we know its adjoint is just equals to its inverse. Okay? And that's why the inverse take this same form. And that's why this is the quantum Fourier transform, the inverse, right? So I think it is correct now. Indeed, it was confusing, but think about this. Any question? Like, let's make sure this is clear.
Yeah, so we see parentheses the matrix, we don't see the parentheses.
Then they are numbers. But if I have parentheses with this index, then it becomes number again. Okay? But that's just my notation. But generally, that's what people do. Yeah. Okay? So we have proved that the quantum Fourier transform is unitary, which is expected because it's quantum gate. We also showed its inverse. It's just exactly the same, except it becomes negative, becomes positive. It switched the sign of the exponent. Everything else the same. Okay? So this one, memorize it, and then later we will use it. Now, let's look at an example, right? Let's find the one-qubit quantum Fourier transform gate. One qubit means what? What is n in one qubit? It means small n equal to 1, capital N equals to 2 to the power 1 equals to 2, right? So what is the size of the matrix? Should be 2 by 2, right? So let's see. So the matrix for the quantum Fourier transform, let me just use comma 1, just my notation, not everyone do this. One qubit equals to 1 over square root of capital N. Capital N is 2 to the power 1, right? You might, maybe you forget, but that is what I remember. Omega, negative 0 times 0. What is this element? Omega what? 0 times what? 1. Omega negative 1 times 0. Omega negative 1 times 1. So it's easy, right? This is 1 over square root 2. Then the first row is what? It's all 0, right? To the power 0, so it must be 1. The first column is also must be 1, right? Because all 0, we already know that, right? In our review here, I already show you this, right? All 1, row and column. This is something you need to memorize. Then what is omega negative 1? Then we need to try, right? So omega negative 1 equals to e to the power negative 2 pi I divided by what? 2, right? So this is equal to cosine pi plus cosine negative pi times I sine negative pi. Make sense? What is this? Negative 1, right? Cosine pi is negative 1. What is this matrix? Huh? No. This one looks like creating superposition, right? What matrix is this? Hadamard, yes. So it turns out that the one qubit quantum Fourier transform gate is the same as the Hadamard gate. Not surprising, Hadamard gate is creating superposition when you apply to a basis state. And quantum Fourier transformation also do superposition as what it's supposed to be. So for one qubit gate, it is the same. Is that okay? Any questions? If no, then we can go to 2 qubit, right? This is just a pure exercise. What is 2 qubit gates then? First of all, what is lowercase n? 2. What is capital N? 2 to the power 2 equal to 4, right? So what is the size of the matrix? 4 by 4. So I will expect is QFT 2 qubit equals to 1 over square root 4, 2 to the power 2. Then I have how many elements? 4 by 4. And I already know that, right? You can go through the math, but I'm trying to show you how to get it easily. 1, 1, 1, 1, I knew that already. 1, 1, 1, I knew that already, right? What is the relationship when you go from here to here? Forgot? Take a look. What's the relationship when we go from here to here? Maybe this is difficult to see. We can even look at this. Relation go from here to here. From one row to another row. You times omega to the power of that column, right? And same from going from left to right, you times omega times the power of that column, right? So my goal is that I need to find out what is the omega in this case. Omega equal to what in this case? Negative I 2 pi over 4, right? Which is equal to cosine negative pi over 2 plus I sine pi negative pi over 2, right? What is this? Cosine pi over 2 is what? 0, right? Negative sine pi over 2? Negative 1. Right? So each omega has negative, the difference of negative 1. Right? So if I go from here to here, it's multiplied by one more omega, right? Because this is the first row. Right? It is 1 times 0, 1 times 1, 1 times 2, 1 times 3. So I go to the right, I multiply by another negative 1, which is going to give me what? Negative I times, negative I, right? Omega is negative I. Now I need to multiply this by negative I. What is that? Yeah. No. So here we multiply by omega. Maybe I should not do that, right? I hope that when you guys watch the movie.
Are you going down?
No, going right, going right. Negative I times negative I is minus 1, right? And then multiply negative I again. Plus I, yes. Let me check. Yes, plus I, right? So I'm done with this row. If you don't like, you can definitely use this equation, right? Which is this part, which is just equals to, what is this? Omega negative 1 times what? What?
1 times 4.
What? 3, yes. Yeah? 1 times 3, right? Because n minus 1, right? You will get that. Oh, yeah, I could have done that, but this is easy, right? I need to find the omega anyway. You need to first find the omega. You are talking about this one?
Yeah, so instead of omega minus 1, I would have
No, omega minus 1 is not equal to minus I, equal to minus 1 here, because omega is different when you have different number of qubit. The capital N is different, right? Yeah, that's a good question. Be careful about that, right? Now, if I go down, this is the same, because, and I also know that this must be symmetric, right? This is wrong. This is a symmetric function, right? Because, not necessarily, actually. It's symmetric because based on this construction, because I times j equal to j times k equal to k times j, so I can get this, right? And then I will continue on this. How about from here to here, right? This one I'm going to have, actually, I'm going to multiply this one from here to here, because it's second row. This is like omega square, right? The difference. From here to here is omega. From here to here is omega square. Okay, so what is omega square? We already know that it is negative 1, right? So negative 1 times negative 1 is going to give us 1. Okay, you're going to multiply this one by omega square. And then multiply by omega square again is negative 1, right? I can even say that omega square equal to negative 1 here. Omega cube equals to what? Just multiply. What is negative I times negative 1, right? So what is that? It's equal to I, right? So here I am going to multiply, and it is correct, right? 1 times I, and then the next one is negative 1, right? Because I times I is negative 1, and then times I again is negative I. Okay, so this one gives us the 2-qubit quantum Fourier transform. Okay, 3-qubit, 4-qubit, you need to do that, and indeed it is not straightforward. Okay, do not think that is easy, but But we don't need to do that. Let the computer do that. Okay. So we will stop here for today.